Okay, we did say 2:30, so I think 13 minutes is good. I was thinking about giving 2 more minutes, but on the other hand, I'm just standing here. I just realized. Uh, hello everyone. After the session that was talking mostly about the methods, since the title of the tutorial is explainability in industry, of course case studies are really important, and we will be going over I think 4 case studies and a demo afterwards. At least in terms of we will present a demo. I'm Shahin from LinkedIn AI, and I will be giving 3 case studies from LinkedIn. So before we go into that, there are methods of explainability, of course, to explain what a machine learning model does. But in industry, a lot of the time, what we want to do also is to be able to collect this data. And in real time, most of the time, when we actually push a product and it starts running, maybe before you can collect the data, but what's even more important is when the data is, all of these models are working and we are serving customers, we want to be able to collect any information about what goes wrong in the system. So you can think of it as explaining what a system does. So we will actually be going over not just machine learning explainability here, but we will also be talking about a system that we use at LinkedIn quite heavily as our 3rd case study. So let's go to the first one. So this is a use case for LinkedIn talent search. Since these case studies are not just the work that I did or anyone in particular did, we decided to also show the people who actually came up with this case study and what they have done to give them proper credit. So this is a joint work between myself, Varun, who actually gave part of the presentation before the break, and Girish. By the way, sorry about my voice. It's just trip and all of that. So hopefully I will not be able to, or I will be able to finish this. So what is talent search? So at LinkedIn, we talk a lot about talent search. We publish papers talking about how talent search at LinkedIn works. And it's not the talent and LinkedIn searches, but rather it's a product that we provide so that companies can actually fill the positions that they require for a job that needs to be done, right? So you might be looking for a software engineer in San Francisco with a specific skill set. And LinkedIn Recruiter would be the product that you would use in an enterprise setting. What a recruiter would do is, or a hiring manager would do is they would use this product, they would go in and enter, whatever query that they want to source candidates for. Again, as I said, something like software engineer with Java skills residing in San Francisco. And then what we do in the system is, it's a 2-phase, the classic retrieval and ranking system. Basically, what we do is over multiple searchers, we filter candidates, and then the candidates that actually fit this criteria is further specialized for the user that is actually searching for these candidates by multiple levels of machine learning models that is trained using our offline data. Now, so what kind of modeling approaches we use? We have been using, naturally the start of the lifetime of this product has started with, listwise, linear approaches, etc. But a couple of years ago, we passed on to the gradient boosted decision tree models. In specific, we have been using pairwise XGBoost quite heavily. And, it aims to rank candidates and try to understand which candidate is better than another, and the whole pairwise error function that it's trying to improve. In our case, the optimization criteria is actually a 2-level interest. It's not necessarily that the user was interested in the candidate and tried to outreach, trying to just have this candidate start an interview process or join their company. But rather, it's that once this outreach happens, that it ends in positive response from the user. So that's what we call in-mail send and in-mail accept, and we train our models using in-mail accept as the positive label. Now, we did get quite good results with XGBoost, and then for personalization purposes, we have been also using generalized linear mixed models. And I'm going to be going into just a bit detail. I don't want these case studies to be talking about the models, but rather what we have applied to explain these models. And then recently, an effort has been to actually apply deep neural nets using the TensorFlow. So during XGBoost, we were basically, what we were doing was we were mostly doing, if not always, looking at global explanations. So basically, that would mean that once you train a model, we would actually, for the specific training of the model, we would actually look at which features were the most important features. These, the anonymization of feature names, feature IDs is something that you will have to see during the presentation because, because of company policy, we do this. But, it's actually a pretty simple visualization. And, as, Varun and Ankur and Krishna talked about before the break, this is over the whole cases or over the whole set of candidates that we ranked and how much each feature actually contributed in a global sense. Now, this is actually nice for the reason of improving models. So since we are in industry and we are trying to give the most relevant experience to our users, our explainability, the explainability which we apply, mainly is due to us, the AI engineers, to understand what the model is doing and whether what we are doing makes sense, whether some features that we are adding make sense, and how we can, it's meant to drive how we can improve these models. And that is what, how we use the global explanations for the gradient boosted decision trees. So there are 4 points. One is we definitely want to understand feature digressions. So suppose you have used a specific feature, some days ago, some weeks ago, and then you realize in the importance, the ordering of the importance, this feature is no longer being picked up. Now, this is actually interesting because you know that even intuitively, this feature might actually be relevant to the performance of candidate selection and the feedback that we get in terms of in-mail sends and accepts. But it's no longer important. So this actually gives us the motivation to do a deeper digging into the system to understand what happened to this feature, whether we stopped collecting it, whether there was something as simple as whether there was an issue with the service that was returning, whether they changed something on their backend and this feature is no longer useful. Now, the second thing that we would look into is that because the team is big and the team is trying to add many features at once, not necessarily everybody separately, introduce one feature and tries to do an experiment with that feature, and you cannot necessarily tie it directly to that feature that you are adding if something has improved. So if you do multiple features, this actually global explanations, rather than the singular cases, gives an idea of whether this feature was worth adding. Something also that is more relevant to the industry cases. Suppose we have real-time features. Real-time features meaning that we compute something about a user's behavior for the past 3 hours or for the past 6 hours. That also means that we have to actually compute this feature quite commonly. And if it's a real-time, full-on real-time feature, we have to actually send a request to the service that provides this feature in real time, which would add to the SLA of the model and how long it would take when you are actually serving candidates with this. This way, we can actually try different granularity of these features, and then we can understand whether we want to keep part or half of these features. This part I myself have used quite commonly. Also, we want to separate the factors that caused an improvement. So, for example, you might be doing multiple things. You might be adding a feature. You might be changing the labeling strategy. You might be adding more data from different segments of users. segments of recruiters, and which one actually caused it. If there was no change in the importance of features, then you might actually think, it's possibly some other reason. So you might want to dig and understand that. And the shortcoming is just with every global view, global explanation, it doesn't give a case-by-case analysis. And for that, you would have to actually see which nodes are activated in the tree. So this global view is not necessarily useful. Another model that we have used is generalized linear mixed models. This would be an example of an inherently explainable model. It's a linear model, but it's personalized in the entity level. So you can think of it as we would have a global model, global linear model that we might use in the case of cold start. But then what we could also do is we could train based on the residuals in the entity level. We could train a recruiter level model using same or different features, as well as we could train, let's say, a contract level model. Contract level, you can think of it as a proxy for a company. Sorry, as a set of recruiters. So this kind of feature, this kind of model actually has a lot of parameters. If you think about the, tens of thousands, actually hundreds of thousands of recruiters and as many contracts, we are actually training these different weights for each and every entity for the same or the different features. But it is inherently explainable no matter what. So meaning that if you give me a case, I can understand exactly for a given entity ID, for a given recruiter, and for a given contract, I can actually combine these linear weights, and I can understand for this case what was important, which is actually good for both the case-by-case analysis, and for globally, you can actually check which entities are seen in what kind of frequency within the app, and actually you can see the contribution of these features as like you can average it out over different entities. Yes.
So either for the case, for attributes or linear
Yeah.
models, how do you deal with the correlation between different features, which might make one feature is important, but the other feature seems not, but actually they are closely correlated?
So we don't necessarily deal with it too much. I understand your question. I think these don't look into it, as far as I know. Because, I mean, it's a linear model, so you're basically looking at the weights in the case of GL mix anyway. For the tree model, I think it's mostly based on how many times a node which actually decides based on a specific feature is fired during the classification or ranking process. So I don't think that's addressed here. So, and the next step, we have personalized mixed models, linear mixed models, and XGBoost, pairwise XGBoost models. And a natural next step is what we have recently done. And when I say recently, it's like within the year period, is that we have been applying deep neural nets with a lot of success as well, improved our metrics quite a bit. And for this purpose, for explaining that, we have been actually using the integrated gradients. Now, people were used to actually the XGBoost coming up with its, the standard tool, looking at the feature values, and people did, the people who actually did the deep neural net work kind of lost that touch, right? So we definitely needed something to understand what a deep neural net does and how we actually use different features. And for that purpose, we have used the integrated gradients method that was in detail explained before the break. And we do use baselines. Baseline, I mean, in integrated gradients is supposed to be a neutral example. And in our case, of course, we can potentially make all the features that we utilize for ranking to be zero.